Video 7. We are going to turn our attention now, instead of looking at the surface area of all of our curvy shapes, cylinders, cones, and spheres, we are now going to focus on the volume of these shapes. Now, in my opinion, volumes of these shapes are probably going to be easier to calculate than the surface areas, because there's really just one main formula for each particular shape's volume. Instead of with surface area, you had, multiple surfaces, and you had to add multiple things together to get surface area. So I think you guys will like the volume stuff better than the surface area. Now, first off, for any prism, and what I mean by a prism is that I have some three-dimensional object that has two bases that are parallel to each other and they're congruent. So for example, in a rectangular prism, or a cube if you will, we can think of the top and bottom bases here as being parallel and congruent. Sometimes our prisms don't have to be standing up on end, they could be on their side. So this, for example, would be a triangular prism because its bases, which are parallel and congruent, are triangles. And so the general formula for any prism is just the area of its base, and I just mean one base, like what's the area of this rectangle, or what is the area of this one triangle, times the whole height of that shape. Okay? So we're going to apply that now to a cylinder. Because a cylinder is like a prism. It's not technically classified as a prism, but it can be thought of that way. Okay? So the area of our base, well, the base of our cylinder is a circle. So we can think of this as the area of a circle and then times the height. So how would we put all of that together? Well, the area of the base times the height, we said, and the base is a circle, so there's our pi r squared, and then the height of it is just our capital H. So this is the whole formula, pi r squared times height. Now, a way for you to think about why this really works the way it does is to think of this cylinder kind of like a building, if you will. Imagine there are multiple floors to this building, which happens to be cylindrical. And all we're really doing is finding the area of each floor of this building. And if we know what the area of each floor of the building is, we then just multiply it by how many floors there are, H in this case. Okay? So if you had like a 10-story tall building, we could find the area of each floor and multiply it by how many floors there are, 10. Okay? So the first example, we're going to practice another one of those rotation problems. It says rotate this rectangle around the y-axis. Again, the vertical axis here is our y-axis. So we're going to rotate this thing around going this way, and we need to think about, well, what type of shape is that creating? Now, this is 5 and this is 7, if you can't tell on your paper there. So what I need to do is we'll just draw it in, why not? So this is going to get reflected on the other side, another 5 by 7 rectangle as it's rotating around. And then the corners end up kind of running into each other. This top right corner spins around, becomes the top left corner, spins around, and we do the same thing on the bottom. They wrap around. So really we end up with a big cylinder. Okay? The 5 in this case is our radius, the 7 is our height. Okay? So if I want to find a volume, I just need to do pi r squared times the height. So the radius is 5, the height is 7. Really, I have 25 pi times 7, which is 175 pi. I don't have any units here, so units cubed to the third power for volume. Now, if you wanted to write that out as a decimal number, whatever 175 times pi is, that's fine. But typically, on standardized tests, the answer is left in terms of pi. So that's the way I'm going to do it. Okay? So again, each circle, if you will, you can think of, we have 7 circles going up this cylinder, and the area of each circle is 25 pi, and then we have 7 total floors in our cylindrical building. So there's a total volume of 175 pi. Now the second problem is going to be a little bit trickier. Okay, so we're still going to do it together here. It says we're still going to rotate. It's the same rectangle, 5 by 7 rectangle, but we're going to rotate it around the line x equals -1. Now, the horizontal axis is our x-axis, and x -1 is right here. Okay, but that's not the line x equals -1. That's the point -1, comma 0. So the line x equals -1 is going to be a vertical line that goes through that point. So instead of this wrapping around just the y-axis, now we're going to take this rectangle and wrap it around this red dotted line instead. Okay? So notice whenever we rotate this thing around, I need to repeat this shape, but I also need to repeat this little gap that's right here. So that has a gap of 1, so there's a gap of 1 on the left side. Okay? And now I'm going to go 5, 2, 3, 4, 5, down 7, and over. So here's my reflected image. And now when this thing wraps around, really this point right here on the top left wraps around to this point right here. And it wraps around back, makes a circular motion. Top right is going to wrap around, hit this top left, and then it continues to wrap around. Same thing down here. We're going to have kind of a little circle, and we're going to have a larger circle. So now we need to picture, well, what is this thing really like? And it's like a roll of toilet paper, if you will. Okay, that little gap there that was right by the line x equals -1, it is kind of like the cardboard tube, if you will. Okay, so we are going to treat this just like it was a regular cylinder, except there's one little piece. So we're going to still think of this as the area of the base times the height. Okay, this is again my generic formula. Now my base, what does my base look like? It's not a full circle. It really looks like this. So I need to be able to find the area of this little tube. Not really tube, of this donut, I should say rather. Now, so if I want to do area of big minus area of small, well, the area of the big circle would be pi times, well, what's the radius of the overall thing? If we start here and we go out, we knew this was 5, plus we had that one more gap. So I'm going to call this capital R, big radius. It's really 6. And now I want to subtract away the small circle. Well, it just had a radius of 1. So here I've got 36 pi minus 1 pi makes for 35 pi. So the area of my base, I'll just erase that, and we'll pop in, it's 35 pi. So each layer, if you will, each floor of the toilet paper roll is 35 pi. Now, how many floors are there, if we will? That's our height. Well, that's still our 7. So I can multiply that by 7, and 35 times 7 is going to give me a volume of 5, carry my 3, 245 pi units cubed. Now, that's one way of doing this problem, is to find the area of the base and multiply it by the height, where the area of the base is, our big circle minus our small circle. I do also want to point out a variation of doing this problem. Now, a second way to do this problem is to think of this as the volume as more of the volume of the whole thing, the whole toilet paper roll, minus the volume of what's not there. And what's not there is where the hole is. So kind of whole minus whole, if you think of it this way. Now, the volume of the whole thing, we still want to do area of the base, but we're going to think of the base as this entire top circle, including the hole in the middle. Okay, so that overall circle on top said we had a radius of 6. So pi times 6 squared times the height of 7, that's going to give me a total of 252 pi once I take 36 times 7. But not everything in that 252 pi exists. There's this cylindrical hole that we need to subtract out its volume because it's not there. Well, the radius of that little guy just had a radius of 1, but it still had a height of 7. So 1 squared is 1 times 7 means we need to take away 7 pi of volume that's really not there. It is in the HOLE hole. And 252 pi minus 7 pi of non-existent volume gives us a resulting volume of 245 pi units cubed once again. So again, you can think of it one of two ways. You can either find the area of the base and find whatever the area of that is, and then multiply it by the height. Or you can take the WHOLE, whole volume, minus any pieces that truly aren't there and subtract them away. Either way is fine. Now, to our next part is a cone. Once upon a time, we talked about the relationship between a rectangular prism, or a cube if you will, and the relationship that it also had with a pyramid that fit perfectly inside of it. So we had something like this. And we wanted to figure out, well, the volume of the pyramid is really what fractional piece of the entire rectangular prism. And so once upon a time, I showed you guys that it took 3 scoops of Kellogg's Raisin Bran. 3 scoops. 3 scoops, 2 scoops. I don't know, they didn't change it to 3 scoops. Anyway, it took 3 pyramids to equal that of the entire rectangular prism. Well, the same principle will apply if we were talking about a cylinder with a cone inside of it. And again, the assumptions that we're making here is that the cylinder and the cone have the same cylindrical base, and they also share the same height. Okay, so it still applies that it will take 3 cones to equal that volume-wise of 1 cylinder. Now, the volume of a cone will therefore be 1/3 of a cylinder, right? If I have 3 cones equals 1 cylinder, I can divide both sides by 3, and I get that cone is equal to 1/3 of the cylinder. Well, we just got done referring to what the volume of a cylinder is. It's just pi r squared times height. So the volume of a cone is 1/3 of a cylinder, 1/3 pi r squared times its height. So to example 3, calculate the volume of this cone. So we need 1/3 pi r squared times the height. And so I look at this cone and I see, all right, well, the radius, it's 9, not a problem. So I'm going to have 9 squared there. Now the height. You might quickly look at this and go, hey, 15's the height. But 15's not the true height of the cone. The true height of the cone is right here. The 15 goes back to our pyramid days, and it's the slant height. Now, there was a relationship between a radius, a height, and the slant height, and that was all conjoined together with the Pythagorean theorem. We know 2 of our 3 sides of our right triangle. So we're going to have to use the Pythagorean theorem. H squared plus 9 squared equals 15 squared. And so we get 81 and 225, and subtract over the 81, and we get that the height squared is equal to 144. And so the square root of that gives us a height of 12. Now a 9, 12, 15, if I divide all of those by 3, this is really a 3, 4, 5 that's been tripled. So if you recognize it was a triple 3, 4, 5, you could have jumped in and said, hey, the height's 12. So we plugged 12 in. And so now we just have to look at all of our numerical values, the 1/3, the 9 squared, and the 12. So if I wanted to look at this, 1/3 of 12 is 4, and 9 squared is 81, and 4 times 81 is 324 pi. My units in this case are centimeters cubed. And there's my total volume of my cone. So just be aware if you are given the actual height of the cone or the slant height. If you're given the slant height, you will have to use the Pythagorean theorem. And the last problem I'm going to leave for you guys is to calculate the radius of a cone when you already know the volume is 100 pi and you know that it has a height of 12. So your goal again is to calculate how big must that radius of that cone be. And that is all for video number 7.